Our last speaker is Masaki Maezawa. We'll talk about technology integration for practical scale quantum annealing machines.
Okay, thank you. Okay, thank you. So I'm Masaki Maezawa, ASD from Japan, and today I'd like to talk about our challenge toward the practical scale quantum annealing machine, especially from the point of view of the technology, the hardware technology. So I don't show any Hamiltonian in my slides, so please forget about your elegant physics or beautiful mathematics for a while. So I start with a very short introduction, and then introduction to the superconductor circuits. And the third part is the main part of my talk. So how to fabricate the practical scale quantum annealing machine. And I will finish with a brief summary. Okay, so everybody here knows that quantum annealing is a promising way of solving the large-scale optimization problems. That was proposed by Kawasaki and Nishimori about 20 years ago, and have been developed mainly by D-Wave. And now the commercial version of the 2000-bit machine is available. 2000 is a great number, but still insufficient, in my opinion. Still insufficient for solving the practical problems, especially in industry. So our goal is to develop the technologies for enabling the practically large-scale quantum annealing machines. So our concept is based on the superconducting circuits and application-specific approaches and three-dimensional match packaging. Okay, so now I will give a very quick overview of the superconducting electronics. So superconductivity shows a lot of interesting and unique phenomena. So these unique phenomena enables the unique functions in the electrical circuits and devices, and they have a lot of the advantages, like, for instance, quantum detections with a high energy sensitivity, almost limiting the quantum, almost nearly the quantum limits. And these examples of the applications: the sensor and detectors, and voltage standards, and digital processing, and of course the qubits. Okay, so this slide summarizes what is the superconducting integrated circuit technology. So the main circuit elements are Josephson junctions, J, and inductor L. This is a kind of the duality with the semiconductor circuits in which transistors and capacitors are main element. So what is the Josephson junction? It's shown here. It consists of the two superconductors separated by the very thin barrier layer. Barrier layer is about even non-superconductor, insulator or normal metals or semiconductors. And this is very important devices because it works as an active device, like a transistor in semiconductor circuits. So usually we use the cross for the symbols. Here shows a simple but very useful example of the superconducting circuits. Two Josephson junction squids. Here, the Josephson junctions and inductors here, and mutual coupling here. This is a schematic layout of these guys. So here are the Josephson junctions, and this branch corresponds to this here, and this the control lines here, and magnetic mutual coupling is here. So to fabricate the superconductor integrated circuit technology, integrated circuits, we use quite a similar technology to the semiconductor LSI. So all the processes are done in the clean room, including the thin film deposition, fine lithography, and etching. And to achieve the good reliability and high yield, so we use the brand materials such as the niobiums for superconductor and SiO2 for insulators. So here shows the example photo of the superconductor circuits fabricated in our lab. The bright part shows the niobium wirings, and the dark part shows the SiO2. So here we have the Josephson junctions, niobium and aluminum oxide barrier, and then niobium. So the structure of the Josephson superconductor circuit is quite a similar one to the MRAM circuit. So there is I think that there is a possibility to use the commercial foundries for MRAM circuits. Okay, let's move on to the quantum annealing machine. Okay, so before determining the technology, we have to consider the architecture of our quantum annealing machine. So now we are using the superconductor integrated circuit technology because this is the most advanced solid state qubit technologies. But now we have a strong limitation of the hardware budget. So even though we use the state-of-the-art niobium-based IC technologies, at most 10 to 5 Josephson junction is available on a single chip. It's quite smaller than compared with smaller than those in the CMOS LSI technologies. So our strategy is simplification of the circuits by reducing the functions. So we intend to quantum annealing machine only for instance, a TSP or a MaxCut or factoring and so on. So this approach efficiently reduces the hardware overhead. And we named this approach the application-specific annealing computing, ASAC. So I like this naming because it's something like the computers in the early stages, ENIAC or ASAC. Okay, so to fabricate our quantum annealing machines, we have a lot of constraints, especially the limitation of the qubits. The number of the qubits on a single chip is critical. So the 1,000-bit qubits is a so big number, but it's still insufficient for practical problems in industry. So the multi-chip packaging is essential to increase the number of the available qubits. And another constraint is that different technologies are required for different circuits. Different circuit means the quantum and the classical circuits. So the low critical current density, high quality, small size Josephson junctions are necessary for qubits and interqubit couplers to achieve the good long decoherence time. On the other hand, higher JC and moderate size Josephson junctions are suitable to fabricate the auxiliary control and readout circuits. So we separate the fabrication process, fabrication technologies for these circuits. In other words, the qubits and the interqubit couplers are fabricated on the different wafer from the auxiliary classical control readout circuits. Okay, so this is our qubits. Following D-wave, so we use the flux qubits. So here is the main body of the qubits, and here are couplers, and also here are couplers. And the direction of the loop current through the loop, superconducting current through the loop, determines, represents the state of the qubits. For instance, a clockwise 0 or anti-clockwise 1. And we use the DC to megahertz range signals to control the qubits and the couplers. So we don't need the RF signal. So this approach will make the system so simple. Okay, here shows the three-dimensional multi-packaging structure we are proposing for our quantum annealing machine. So this packaging structure consists of 4 main components: qubit chips here, and active interposers, this green one, and bridge interposers, and our package substrate. The qubits and the interqubit couplers are densely integrated on the qubit chip, and classical control and read control or readout circuits are fabricated on the active interposers. And bridge interposers are used to connect the neighboring active interposers, and package substrate manages a number of wirings between the low temperature and room temperature stages. So to realize our quick structure, our packaging structure, superconducting flip-chip bonding technology is very important because it can connect the qubit on a chip to the control or readout circuit on the active interposer, and also the qubits on a chip and another qubit on another chip. So this scheme brings scalability for our quantum annealing machine. So, and choice of the materials for substrates for the package components are also important to prevent the collapse by the thermal stress at low temperature. So all the substrates should have the same coefficient of the thermal expansion. The simple solution is the use of the same materials for all the substrates, for qubit chips, the interposers, and the package substrates. So what is the best material for the substrates? From the point of view of the engineering, the silicon wafer is a unique option. But the use of the silicon wafer sets another limitation of the area of the package substrate. So at the present, 300 millimeter wafer is commercially available. So from the 300 millimeter, we can cut out about the 200 millimeter package substrate. In the future, probably within a few years, 450 millimeter wafer will be available, and we can use the 300 millimeter square package substrate. And here shows, here summarizes the fabrication process for the processes for the qubit chip and the active interposer. So the details were already presented by my colleague Hidaka-san sitting here, so I can skip this one. And now I roughly and optimistically estimate how many qubits we can use in the future. So state-of-the-art 3D packaging technology allows a negligibly small area overhead, something like the 1 millimeter. So the total number of the qubits determined by the package substrate area and qubit area. At the moment, we estimate the area of our qubits about the 20,000 square microns, for instance, 100 micron by 200 micron. So this number gives some estimates For instance, on the 100 by 100 millimeter square package substrate, we can integrate 0.5 megaqubits, and 200 by 200, 2 megaqubits, and the 300 by 300, 4.5 megaqubits. And this is the last slide before summary. So here summarizes some specifications of the components of our QUIP three-dimensional packaging. So in the future we estimate to use we expect to use the commercial foundry for MRAM, magnetic random access memory for qubit chips, and the BOL in CMOS technology for interposers. Okay, I'm finishing my talk. So the quantum annealing is a promising way for solving the large-scale optimization. But still the hardware scale is insufficient, in my opinion. So we proposed a scheme of the technology integration for enabling large-scale quantum annealing machine. And at the present, so probably it's optimistic, but we estimate by using our scheme, more than the 1 megaqubits integration will be possible. Thank you for your patience before our coffee break.
Okay, questions? People want a tea. So if you say application-specific architecture, what do you what do you mean by that? Or in what extent?
Okay, so we restrict the connectivity. So we use the fixed couplers.
Sure. Yeah.
So our machine can be used for only for the specific application.
Yeah. Okay. Sure. But the plan is to stake the D-wave couplings as they are now, because that's also an evolving subject, right? So but you're not planning on investigating how to use different qubits or different coupling schemes and so on.
Sorry, I couldn't follow. What is a coupling scheme?
Well, there's a certain these chimera graph connectivity.
Yeah.
The research that you are looking into is the packaging problem only, and not you're taking the basic connectivity, graph connectivity, and what qubits you're using as a given thing.
Okay. So we have to use some kind of the graph. I'm not sure it's a chimera or something, okay, but it's up to the designer. Designer can choose what graph they want to use.
Okay, the packaging doesn't depend on that so much. Okay,
yeah. So the number of 1 million qubits is very large compared to the current technology achieved by D-wave systems. And what makes you different from their limit and your million qubit limit? Why can you achieve such a big number?
Yeah. The big difference is that we will use the multi-chip packaging technology. The number of the qubits, for instance, 2,000 or 4,000, is just a number on the single chip, integrated on a single chip. So to increase the simple way to increase the number of the qubits is to use the number of the chips.
And you connect those chips together to work together as a single processor.
Yeah, I hope so.
Right, because these couplings have to be reliable and strong enough and so on. More questions now. Oh, yes.
Is it using a niobium superconducting qubit? But it seems that lacking coherence time. What is the estimation value of coherence time?
Oh yeah, good point. So probably the niobium qubits with a multi-layer structure has a short coherence time. Probably the 100 nanosecond or something.
100 nanoseconds. Oh, how 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 will you improve it? You think?
It's another problem, another challenge.
Oh.
So we are looking for the good way to increase our niobium, increase the coherence time of our niobium qubits.
Oh. All right, I see.
Okay, I think we should conclude here. Thank you for the last talk.